Have you ever wondered why your computer doesn't easily fall prey to viruses or unauthorized access? The answer lies in the protection mechanisms of its operating system. These mechanisms are a set of rules and procedures designed to shield the system's resources and data from manipulation, corruption, or unauthorized access. Think of them as digital bodyguards, always on the lookout for potential threats. They control who gets to interact with what part of the system, ensuring that only authorized users or processes can access and modify certain resources. This is not just about keeping your personal files safe, it's about maintaining the integrity, security, and stability of the entire system. Whether it's managing permissions or establishing security boundaries, protection in operating systems is a complex but crucial aspect of modern computing. Now that we have an understanding of what protection in operating systems means, let's delve deeper into its key concepts. First on our list is domains of protection. Domains, in the context of operating systems, represent a set of resources along with the permissions granted within it. This could be a user, a process, a role, or another logical grouping. These domains are the building blocks of security, acting as partitions to segregate access rights. Think of it like a house with several rooms. Each room can only be accessed by those with the right key, ensuring that only authorized individuals can enter. Similarly, in operating systems, domains establish security boundaries, ensuring that only those with the right permissions can access certain resources. This domain-based segregation helps maintain system integrity, security, and stability. It's like having several layers of security, each one further safeguarding the system's resources from unauthorized access, manipulation, or corruption. Domains of protection therefore play a critical role in ensuring only those with the right permissions can access certain resources. Moving on, we have access control and permission management. This is the heart of protection in operating systems, controlling who can get their hands on the precious resources and what they can do with them. Access control is the bouncer at the door, checking IDs and deciding who gets in and who doesn't. It's the mechanism that determines who can access system resources and what actions they can perform. This can be based on various models, each with its unique approach. First up, we have Discretionary Access Control, or DAC. This is like a house party where the host decides who gets in. The owner of the resource decides who can access it and what they can do. It's discretionary because the owner has the discretion to grant access. Then there's Mandatory Access Control, or MAC. This is more like a black tie event with a strict guest list. Access decisions are made based on predefined policies and not even the owner can bend the rules. We also have Role-Based Access Control, or RBAC. Think of this as a corporate event. People are granted access based on their role in the organization, making it easy to manage permissions for a large number of users. Now, let's talk about permissions. Permissions are like the VIP passes at a concert, defining what operations a user or process can perform on a resource. Can they read the data? Can they modify it? Or can they run the show by executing commands? Permissions are typically managed through access control lists, or ACLs, a sort of guest list for your resources. Alternatively, they can be managed through simpler schemes like read-write-execute bits in Unix-like systems, a quick and dirty way to control who can do what. So through access control and permission management, we can control who can access what and what they can do with it. This is like having a sophisticated security system for your digital house, ensuring that only the right people can access your precious resources and use them in the right way. Next up are security policies and capabilities. Let's start with security policies. These are essentially the rulebook for operating system protection. They lay out the do's and don'ts for user and process behavior. They're like the traffic rules of a busy intersection, guiding the flow of data and preventing chaos. Security policies can be quite diverse. For instance, some policies may dictate how passwords should be formulated, when they should be updated, or how often a user can attempt to log in before being locked out. Other policies might govern what kind of data can be shared between processes, or how system resources should be allocated. These rules are not just arbitrary, though. They're designed to mitigate potential threats and protect the integrity of the system. For example, a policy that requires regular password updates helps to guard against unauthorized access. Now, let's move on to capabilities. If security policies are the rules of the game, then capabilities are the player cards. They're tokens or references that grant access to specific resources. Think of capabilities as the keys to various doors in a building. Each key or capability gives you access to a specific room or resource. This could be anything from a file, a hardware device, or even a network connection. Capabilities provide a form of access control that's more granular than traditional user or group permissions. They allow for fine-grained control over resource access, enabling a system to manage who can do what with which resource. For instance, a process might be given a capability to read a specific file but not write to it. Another process might have the capability to write to that file but not delete it. This way, each process is given just enough access to perform its function and no more, reducing the risk of unauthorized activities. Security policies and capabilities thus provide a robust framework for ensuring system protection. Now, let's explore the concept of protection rings. Imagine a multi-layered structure, each layer representing a different level of privilege within the operating system. This is the hierarchical model of protection rings. It's like a castle with 4 concentric walls, where the innermost wall, ring 0, guards the most privileged operations, like the kernel of the operating system. The outer rings, ring 1 to ring 3, hold less privileged processes, with each ring having progressively lesser access to system resources. Protection rings create a robust barrier between user-level processes and system-level operations, ensuring that a rogue application or malware can't just waltz into the castle and wreak havoc. They ensure that only the most trusted processes have the most access, while others are kept in check. This separation of privilege helps maintain system integrity, security, and stability. Protection rings, therefore, provide a structured way of managing system access. So, how are these concepts implemented in actual operating systems? Well, the approach varies, but it often involves a blend of hardware support and software-based controls. Let's dive in and explore 3 common mechanisms: user and group permissions, access control lists, and role-based access control. First up, user and group permissions. These are a staple in Unix and Linux operating systems. Each file or directory is assigned permissions that dictate who can read, write, or execute it. It's often represented by a trio of bits for each category: owner, group, and others. Each bit defines the read, write, and execute permissions. It's a straightforward yet effective method of governing access. Next, we have access control lists, or ACLs. They offer a more flexible approach to permission management. ACLs allow for specific rules to be set for different users or groups. You'll find this approach common in Windows and some Unix or Linux systems. ACLs provide a nuanced way to handle permissions, enabling you to tailor access rules according to the specific needs of your system. Lastly, we have role-based access control, commonly known as RBAC. RBAC assigns roles to users, with each role carrying specific permissions. This method is particularly prevalent in enterprise environments where managing complex permission structures is the order of the day. With RBAC, you can easily manage permissions based on roles, making it an efficient way to handle large user bases. All these mechanisms have their strengths and are chosen based on the specific needs of a system. Some systems may use a combination of these methods to secure resources effectively. Remember, the goal here is to ensure that user data and system resources are protected from unauthorized access, manipulation, or corruption. These mechanisms, working together, form the backbone of protection in operating systems. In conclusion, we've traversed the landscape of protection in operating systems, understanding its importance in maintaining system integrity, security, and stability. We've delved into the domains of protection, which segregate access rights and establish security boundaries. We've explored access control and permission management, which are the guardians of who can access resources and what actions they can perform. We've also touched upon security policies and capabilities, which guide protection mechanisms and ensure fine-grained control over resource access. We've looked at the concept of protection rings, a hierarchical model that ensures separation between user-level processes and system-level operations. Lastly, we've seen how these concepts are implemented in operating systems using a mix of hardware support and software-based controls. Remember, a well-protected operating system is the first line of defense against unauthorized access and potential harm to your computer.